Good afternoon. My name is Derek, and today I'm going to be telling you about several improvements we made to our tool, Verbatim. Verbatim is a lexer, and it's parameterized by a list of lexical rules. So as you can see, it takes a string and produces tokens that conform to those lexical rules. Verbatim is verified in Coq, but we wanted to make some improvements to its performance and change its output type slightly so that it would be more amenable to downstream parsers. Jumping right into performance, this is a graph of Verbatim's performance before we made any changes. So on the x-axis, you have the size of the input, and on the y-axis, you have the processing time. This is relatively slow for a lexer. So again, we wanted to make some improvements, and that's exactly what we did. We optimized the performance, not once, not twice, but if we zoom in on that purple line, 3 times. And in doing this, we produced an asymptotically faster lexer, which is functionally equivalent to the verified reference. So today I'm going to give you some background information to help you understand those 3 optimizations. And I'm going to tell you about some additional functionality that we added in the form of user-supplied semantic actions. A note about notation. I'm sometimes going to represent regular expressions as these set bubbles when explaining certain operations. We're going to use lambda to denote the empty string. This is in contrast with epsilon, which we'll use to denote the regular expression, which matches the empty string. And if I was being careful, I might wrap these characters and strings in double brackets to emphasize that they're regular expressions. But I'll only do that when it's necessary for clarity. Here's an example of Verbatim's behavior. It's going to take a string. In this case, it has A's and B's. It's going to take the lexical rules you see below that string, and it's going to produce the tokens on the right. So a lexical rule is a labeled regular expression, and a token is a labeled string. And these labels are provided by the user. Here's the formal definition of the Brzozowski derivative. We use this for regular expression matching. Just to explain it by example, if we have the regular expression represented on the left and we take a derivative with respect to C, that operation intuitively eliminates all of the words which do not start with C, and it removes the leading C from the remaining words. And this is great for regular expression matching. If we want to know if a string matches a regular expression, we're going to take a derivative for each character in the string. So if we have this regular expression, we can see that it has the word cat in it. And the way we check that match programmatically is we take a series of derivatives, C, A, T. And if we followed the word cat as we made these transformations, we would lead directly to this lambda. So the final regular expression matches the empty string if and only if the initial regular expression matched cat. And I think that's enough for you to understand the first optimization. So a major shortcoming of the naive lexer is that it does direct regular expression matching. And this is bad because this is sort of the base operation and this derivative operation. And it might be the case that we take the same derivative many times, and we have to compute that from scratch. It's also a problem because we have to compute these derivatives during runtime. There's no ability to do any pre-processing because we don't know what the string is, and so we can't anticipate which derivatives we'll need to take. And so the solution, sort of, is to just take all of the derivatives and store them in a table. And this is the transition table, actually, for an equivalent automaton. And this is a nice construction due to Brzozowski. It says regexes are states, and you determine transitions by the derivative operation. So at the top, we have the regular expression E. If we want to take the transition on A, we're just going to point to the state labeled with the derivative of E with respect to A. And this automaton is right now depicted as a tree, but in general, it's just a graph because equivalent regular expressions are represented by the same state. So this construction is implemented in Coq, and so a challenging aspect of implementing this construction is we have to prove that it terminates. Now, Brzozowski showed that if you start with if you start with a regular expression and you take derivatives, you'll only ever reach a finite number of regular expressions, up to some notion of equivalence. We don't formalize this proof due to Brzozowski, but we do reference it when we determine this depth here. This depth is essentially the recursion depth of our construction. So we don't formalize Brzozowski's proof, but we do reference it. Now you might be wondering, what if your transition table is incomplete? You don't formalize Brzozowski's proof, so how do you get around that? And we sidestep this by defaulting back to the on-the-fly regex matching strategy if we ever encounter this empty cell situation. So in terms of correctness, we know that taking derivatives in this way is valid. We know this because of our reference lexer and its proof. So if we default back to the on-the-fly regex matching, that's perfectly fine in terms of correctness. Otherwise, we're going to use this table when we can, and we're going to maintain the invariant that non-empty table entries have derivatives. And this is sort of just by construction. And I want to emphasize that the situation where we have empty entries, it's a performance concern, not a correctness concern. And in all of our experiments, we didn't run into the situation where we had an empty entry. And as you can see, performance improved drastically. So now I'll tell you about the second optimization. The second shortcoming I want to talk about involves this helper function called maxpref1. Now it finds the maximal prefix of a string with respect to a derivative or a lexical rule. And the issue with the development is that we sometimes call this function with the same arguments, and this can be very expensive. So here's an example call stack. Now the goal of these columns is to compute the value at the top, this lex function. All of the calls below that are in service to this lex function. So if we can eliminate calls and still get the right value, that would be lovely. So you'll see in red that we're making some redundant calls. We compute the same thing in 1.4 and 2.4 and the same thing in 1.5 and 2.5. If possible, we would like to not make redundant calls. And so we're going to use memoization for that. We're going to maintain a memo. We're going to perform lookups. If the entry is empty, we're going to compute the value from scratch. Otherwise, we can just use the value that's there. So here's the call stack again. Here is a representation of the memo. And let's zoom in on these last calls in the columns. So what's going to happen is we're going to make the call in 1.4. In order to compute that value, we have to make the call in 1.5. And then that value will propagate up the call stack. But the point is, when we compute that first column, we're going to fill in these entries in the table. And now we're going to compute the calls in the second column. And when we make the call in 2.4, because we're not computing it from scratch, we're looking it up in the table and using the value that we got in 1.4, we actually don't even need to make the call in 2.5. We can completely eliminate that. You can imagine that these call stacks can get very deep. And you can't see it in this example because it's a pretty shallow call stack. But in real life situations, you might make a lot of recursive calls. And if you can eliminate that, you get huge performance gains. So in terms of correctness, we know that the unmemoized version of the function is correct. And that is the version that we're using to populate the table. So we know that the memo is correct. All of the values that are non-empty are correct. We maintain that invariant. And so when we do lookups, we get the correct value. Therefore, the memoized version of the function is correct. And as you can see, huge performance and gain improvements. For the largest data point depicted, the purple graph is 20 times less. So the next optimization has to do with the way we are representing our memo keys. Each of the row labels you see highlighted is, each of these is a suffix of the input string. So these keys are linear in the size of the input string. And in order to do lookups, we have to read these keys. So at best, the performance for a lookup is, big omega of n. So what we're going to do is we're going to represent these keys more efficiently. Because they are all suffixes and there's only one suffix of each length, rather than representing these suffixes by what they are, we're going to represent them by their length, encoded in binary. And this is really nice because now we can use these structures called binary tries as part of our memo. So on the left, we have our memo, and I've highlighted a column in yellow. This column is labeled 100, this row is labeled 100. And so if we follow 100 in the tree on the right, we end up at that yellow box. And that yellow box represents the column highlighted in yellow. And this is some data structure that maps regular expressions to strings. But a nice thing about this structure is it doesn't matter how densely populated this trie is. We only ever have to do one operation for each bit in the key. So in terms of correctness, it's pretty straightforward. The row designated by the ith suffix is equivalent to the row designated by I. So these tables are equivalent up to renaming the labels. And here we see the performance for the fully optimized version of Verbatim. And we really wanted to stress test this, which is why the x-axis changed. We wanted to give it much larger inputs. And it takes a matter of seconds to compute these values. And if we were to run the naive version of Verbatim on these inputs, as you can see, it would take ages. So very happy with the performance improvements. Now I'll tell you about some additional functionality added by semantic actions. Here's a motivating example. Let's say that Verbatim needs to lex a sum of digits, for instance, 2 plus 2. Verbatim, as I've explained it so far, would just produce these labeled strings. But wouldn't it be nice if instead of the string 2, we had the integer 2? And that's exactly what this improvement to functionality allows us to do. So the user, they supply the labels to us. And so it's not unreasonable to ask them to supply some additional information. In particular, they're going to supply a mapping from each label to a type. And then they're going to tell us how to take a string and convert it to that type. So Verbatim is going to just produce these labeled strings, as I've talked about in the past. And then it's going to add an additional layer where it applies the semantic actions provided by the user. And we wanted to verify that adding this extra layer did not impact performance. And indeed, there's no significant difference between Verbatim with or without semantic actions in this case. Of course, the user might provide semantic actions of arbitrary complexity, so it's hard to make runtime guarantees. But if the semantic actions are reasonable, we've shown that they will not affect performance significantly. So in conclusion, I've showed you how we took a verified reference. It's a naive, slow reference, and we optimized it. And at each optimization, we showed that it was equivalent to the naive reference. And this methodology, this refinement-based methodology, it did us a lot of service. We were able to prove these very well-optimized programs were correct using this methodology. That's all. Thank you, and I'm happy to take questions.
Thank you, Derek.
Thank you.
So we already have a question on the Q&A channel, so I'll go ahead and start reading that. And hopefully if anyone has any questions in the room, they can signal our volunteers there. So Dan Fruman from the University of Guggenheim asks, what do you do when you cannot provide a total function from strings to t? For example, what would you write for the integers?
I guess I'm not sure why you couldn't do a total function in that case. I guess, okay, so if it's not like a well-formed integer in the form of a string, the token will just spit out like a failure value, like none, and that would be reported back to the user. Perhaps as future work, we could create some sort of correspondence between the lexical rules and the semantic actions, where well-formed strings are guaranteed to output not failure values. But for now, it's just an error that's reported back to the user.
Okay, thanks. Are there any questions in the room?
Doesn't seem so. So, last chance.
So I guess I'll ask a question. So if I understood it correctly, you were using binary tries to implement this memoization table at the last step. Have you thought about using like Coq support for primitive arrays and integers? Because presumably those would have constant time lookup for keys. Do you think that would improve things, or?
So I guess no matter how we represent the keys, at the end of the day, we're going to have to read every bit in the key. And as far as I can tell, binary tries would, produce the same performance as these arrays. Because all we're doing is reading the key, and you'll have to do that no matter how you store the information. There is one final optimization that could be made, though, in order to obtain constant time lookups as opposed to log n time lookups. And that involves this key insight due to reps. And he realized that when you're doing lookups, the lookups are always in sort of adjacent rows. So you can always just do a plus or minus one, like shift a cursor up and down the table, and then you would have constant time lookups. So that's how you can do that.
Do you think doing that would lead to a significant improvement or over what you have right now?
I'm not sure that it would, honestly. These keys they're log n in the size of the input, and it's not obvious that it would be a huge performance increase, but it would be linear time. So it might be worth it.
Okay. Thanks for answering that question. Are there any other questions in the audience there?
No.
Okay. Well, in that case, let's thank Derek again. Very nice talk.